It's a pleasure to welcome today's speaker, Amin Gohari. Amin did his undergraduate degrees at Sharif University, and then he went to UC Berkeley for his PhD. And then he returned to Sharif to be on the faculty of the Electrical Engineering Department. And recently, he's joined the faculty of the Tehran Institute of Advanced Studies. Amin's research interests are in network information theory, and one of his specialties is to develop new methods for proving coding theorems in information theory. And he has been doing with a number of colleagues, including Chandra Nair at the Chinese University in Hong Kong. And I think Chandra is on the online today. So for instance, in the area of achievability proofs, they've looked at maximal correlation, which gauges common randomness and its connections to hypercontractivity, then output statistics of random binning, and then the properties of entropy functionals that are associated with auxiliary random variables. And in the area of converse proofs, they've been looking at here, Amin and Chandra have been looking at dissecting entropy functionals and looking at their subadditivity properties to show that the optimal regions associated with product models can be strictly superior to a suitable combination of component models. So one thing I have observed over the years in the work that Amin does, and this is true of Chandra Nair as well. So for Amin to work on a specific problem in information theory, it must pass a litmus test. That test being that some of the best information theorists in the world should have worked on the problem and failed to solve it. Only then will Amin work on that problem. And with that, I hand you over to Sagnik, who will explain why, for technical reasons, today's seminar is being conducted slightly differently. And then, of course, we look forward to Amin's talk. Welcome, Amin.
Hi. So to get around some technical difficulties, the way we are going to do it today is that Professor Gohari has sent me the video of his talk, and it's in 7 parts. So I'll play the 7 parts one by one, and every 10 minutes or so, when the part changes, we'll pause for questions. And yeah, so if you have some short questions about what he talked about like a minute back, then you can ask it there. If you have more general questions, we'd prefer if you wait until the end of the talk. So yeah, let's start then, if no one has any other questions.
Hello and welcome to my talk. First, I would like to thank the organizers very much for inviting me. The title of my talk is The Auxiliary Receiver Approach in Network Information Theory. This is joint work with Chandra Nair. Since this is a teaching seminar, I have planned my talk for students who have taken perhaps a first course in information theory. However, at the end of my talk, I will have a discussion for the experts. This is the plan for my talk. First, I will discuss the type of results that I will present. Then I will have a quick overview of properties of mutual information. Then I will get to the auxiliary receiver approach, first for a point-to-point setting, then a relay, then a broadcast, and finally an interference channel. So the purpose of this talk is to give a new technique to prove infeasibility results. And what do I mean by infeasibility result? So consider a point-to-point channel with input X and output Y, and a channel PY given X. We say that a rate R is achievable if for any arbitrary epsilon positive, there exists a code of rate R whose error probability is less than epsilon. Shannon proved that there is a fundamental limit called channel capacity, which is equal to maximum over P of x, mutual information between x and y, such that if R is less than C, there is a code with arbitrarily small error probability, and if R is greater than C, then there is no code with arbitrarily small probability. Now, this second statement is an infeasibility statement. The first one is an achievability result. So in this talk, I will only discuss infeasibility statements. In the case of point-to-point channel, we are lucky that our infeasibility result exactly matches the achievability results and complements that. In general, if we have multiple transmitters and multiple receivers, the set of rates or the rate or set of rates that we can prove are achievable, set of rates where we can design codes for, is strictly inside the set of rates where we can exclude as being achievable. So developing techniques to strengthen, to allow us to have better infeasibility results is motivates this work. Okay, given two random variables x and y, I just want to remind you that mutual information between x and y is defined as follows. Conditional mutual information is defined again similarly. And mutual information has this property, it's called the chain rule. And this property, chain rule has some interesting implications. For instance, consider the following. Suppose I have a random variable m, a sequence of random variables x1 to xn. This is just some arbitrary sequence of random variables. And another sequence y1, y2 to yn. Then mutual information between m and the entire sequence x. So xn denotes the entire sequence x. I also show it by x1 to n. Minus mutual information between m and yn. It's equal to summation j from 1 to n, mutual information between m and xj, given x indices 1 to j minus 1 and yj plus 1 to n, minus mutual information between m and yj, given past of x and future of y. So here x1 to j minus 1 is just x1 to xj minus 1, and yj plus 1 to n is yj plus 1, yj plus 2 to yn. Okay, this identity follows from the chain rule. It's a non-trivial use of the chain rule, but you can just expand both sides and see that it holds. One way to see it is to write this difference as a telescopic sum. So we can write this as mutual information between m and xn minus mutual information between m and x1 to n minus 1 yn plus mutual information between m and x1 to n minus 1 yn minus mutual information between m x1 to n minus 2 yn minus 1 to n, and we can continue that. and write plus mutual information between m and x1, y2 to n minus mutual information between m and the entire sequence y. Then if we simplify each of these differences, we get the expression that I have written on the right hand side of this equation. Okay, so this is one identity that I'm going to repeatedly use later on in the talk. There are two more identities. So here in this identity, observe that I have x1 to j minus 1. So if I'm standing at index j, 1 to j minus 1 is the past of x, and yj plus 1 to n is the future of y. There are two more identities that involve this past future random variable. So this, the mutual information between past of x and future of y, if we compute this mutual information with the current value of x and subtract the mutual information with the current value of y, this difference, if we expand the terms and do the algebra, it simplifies to what I have written here. And what are the meaning of these terms? Mutual information between past of x and the current value. This thing, summation j 1 to n, I of x 1 to j minus 1 and xj, it equals summation j1 to n, entropy of xj minus entropy of x1 to xn. And this one can also be written as summation j1 to n, I of xj plus 1 to n and xj. So for instance, so mutual information between the past of x and x is equal to summation of mutual information between future of x and x. So this second term, I can also write it as summation over j. I can also write it as mutual information between y 1 to j minus 1 and yj. Okay. There is one last identity you can see here. This identity is known as the Chisar-Sum lemma, and it's equivalent with the identity that I have written above. So if you look at this, you can just observe that on the right hand side I have past of x and future of j, but then I have these terms swapped on the other side, and instead of yj I have xj. Okay, because these three identities are important and I'm going to use them repeatedly throughout the talk, I would like to pause here and see if there are any questions about them. All right, so I want to discuss the use of auxiliary receivers for a point-to-point channel. So a point-to-point channel, in a point-to-point channel we have an input x, we have channel p y given x, and an output y. The capacity for this channel is known. It's maximum over px I x y. The converse that we have matches the achievability result that we can prove. So this problem is completely solved. So there is no hope of getting any new converse for a point-to-point channel. However, I would like to discuss the auxiliary receiver for this point-to-point channel just as a warm-up. And because this is the simplest setting that we can consider. So we'll see what we can get, but we should not expect anything surprising here. But let's do it. So what do I mean by an auxiliary receiver? So here Y is a receiver. I can consider, instead of a joint conditional distribution of Y given X, I can consider P of YT given X, where T is some other receiver. So this is my auxiliary receiver. Okay. So T is the output of Y and T are the outputs of a memoryless channel with input X, and it's defined, T is defined through this conditional distribution of YT given X. So, so let me write how the standard converse for a point-to-point channel works out. So suppose we have a rate R and a message M, which is a number in the set 1, 2 to the 2 to the NR. This M is mapped through an encoder to a sequence XN. XN is sent over the channel, so we get YN and also TN. And then YN, we apply a decoder here and get the message M hat, the reconstruction M hat. And when we want to prove a converse, we start with NR equal to entropy of M less than or equal to, well, this is approximately equal to I of M and YN by Fano's inequality. Then using data processing inequality, I can write this is less than or equal to XN and YN. And this is equal to entropy of YN minus entropy of YN given XN. Then this term I can write entropy of YN minus summation entropy of YI given XI. And now I can write this as summation entropy of YI minus entropy of YI given XI plus entropy of YN minus summation entropy of YI. So I'm adding and subtracting summation entropy of YI, and then this term is summation mutual information between XI and YI plus entropy of YN minus summation entropy of YI, and this one is less than or equal to N times C plus entropy of YN minus summation entropy of YI. Now, this last term, we know that it's always less than or equal to 0. That's a property of entropy. Entropy of joint entropy is less than or equal to sum of the individual entropy terms. What this converse also implies is that if we have a code where R is close to C, then this term, entropy of Yn minus summation entropy of Yi, should be approximately 0. So this is the term that we are dropping. This is less than or equal to NC. So this term has to be approximately 0, which means that Yi's are almost IID. Okay, this is for any arbitrary code with rate R, which is very close to capacity C. Okay. Now, So I can introduce, now I'd like to introduce the auxiliary receiver T. I can do that in two ways. One is, okay, so here I'm dropping this term entropy of yn minus summation entropy of yi. What I can do is, let me not drop this term, and I can add the term corresponding to j here, so h of jn minus summation h of ji, and then plus, sorry, minus entropy of jn minus summation entropy of ji. And then I can drop the green term instead of, so this term is less than or equal to 0. So instead of dropping the term for y, I can drop this term for j. And then I would have to take care of this difference. Okay. Observe that up here, and some of the individual entropies minus the joint entropy, I can write it as mutual information between the past and the current value, or the future and the current value. And when I have two sequences of random variables like x and y, I can look at the difference of basically mutual information between past and the variable, and there is an expansion for it, right? So I can try to use this and see if it's going to be helpful, but this is one idea. Now, another way to introduce the auxiliary receiver is, so I'm not going to do this here, but let me tell you another way that we can introduce the auxiliary receiver here. So if you look at this chain of inequalities, okay, we're not using the fact that yn decodes m in this chain of inequalities. So let me erase this first part, and maybe, yeah, and let me erase this also. So we're not using the fact that yn decodes m here. So if I replace yn with tn, okay, everything goes through. Tn, ti, ti, tn, ti, and let me erase this last part also. Okay. So, but I'm interested in mutual information between m and yn, so I can write this as mutual information between m and tn plus mutual information between m and yn minus mutual information between m and tn. Then I can use the upper bound above for mutual information between m and tn. So this would be summation I of xi and ti plus entropy of tn minus summation entropy of ti. And for this second term, if you remember, I told you an expansion. So this would become summation over I of m, and yi given y1 to I minus 1, ti plus 1 to n, minus I of m and ti given y 1 to I minus 1 and ti plus 1 to n. Okay, so I'm going to manipulate this a little bit. So observe that xi is a function of m. So we know that m implies xi. So I can throw in xi here next to m, and then one can show that, well, I'm not, just believe me that I can write this in this, the above equation in this way: xi ti plus entropy of Tn minus summation entropy of Ti. I can drop m from this equation, so this becomes mutual information between xi, yi, and y1 to I minus 1 Ti plus 1 to n minus I of xi Ti given y1 to I minus 1 Ti plus 1 to n. Now let me call this variable ui. Then again, some algebraic manipulations show that I can write this equation in this form: summation mutual information between xi and yi plus I of ui and ti minus I of ui and yi plus entropy of Tn minus summation entropy of Ti. Okay. Now, this last term, first term, we know that this is less than or equal to nc, so I get less than or equal to nc plus this term, sum of these terms. Okay, now, if I know that the channel y is stronger than the channel t, receiver y is stronger than t, in the sense that it's called less noisy. So if y is less noisy than t, I'm not going to define it, but what it means is that assume that receiver y is stronger, so this mutual information between ui and yi is larger than mutual information between ui and ti, so this term is less than or equal to 0. So if y is less noisy than t, then I can write this as less than or equal to nc plus h of tn minus summation of h of ti. And now I know that nr was less than, so I can start nr less than or equal to I of myn. What I can conclude from here is that if I have an arbitrary code, right, an arbitrary code that is whose rate r is approximately equal to c, then h of tn minus summation of h of ti should be approximately 0. Okay, which means that TIs are also almost IID. Okay, so it's not just that outputs of Y are almost IID, but if Y is less noisy than some receiver T, then TIs should be almost IID too. This is for any arbitrary code that is closing to capacity. whose rate is close to capacity. So anyways, we cannot get a new upper bound, but we can make some observations here. So I'm going to now discuss the relay channel. So this was part 2. The more interesting part is when we consider a relay channel. To summarize, what I did was I just, in one approach, I just take whatever converse I had for y and I replaced y with t, and then I added this penalty term, and then I expanded this penalty term via the identities that I introduced earlier. The other thing that I could do was to look at the terms that I'm dropping in the converse and try to write the corresponding term for auxiliary receiver and drop those terms instead of dropping the term for the original receiver y. I'm going to pause here to see if there are any questions, and then I will continue with the relay part.
Hi, Amin, this is Prakash. May I ask a question? Hello?
Sure.
Yeah.
Yes.
I mean,
Yes.
the standard proofs, the converse proof, for instance, it can be done using a single shot approach and then extended to the n-fold case, right? Now, this particular approach that you have outlined hinges very much on a latitude and time in I going from 1 through n. So the question is there a single shot version of this approach? And if so, what would it be? Thanks.
So by single shot, you mean like if you have just one, like the one shot in for results?
That's right. Yes, that's right. Yeah, that's right.
We have not done that, but that's an interesting question. I have not looked at that. Yeah, I don't know. Maybe Chandra can, he might have something to say, but I haven't looked at that. That's a very good question.
Thanks.
Okay, let us continue with the relay channel. So a relay channel is a terminal with 3 nodes, a transmitter, a relay node. So this is the relay node, and a receiver. This is the transmitter. So the transmitters and the relay node, they both have inputs to the channel. So transmitter has input X, relay has input XR, and both the receiver and the relay node get outputs from the channel. So these are the inputs to the channel. Relay gets YR, receiver gets Y. And this channel is described by a conditional distribution Py, Yr, given X, XR. This conditional distribution describes the output of the relay and the receiver conditioned on what the transmitter and the relay are sending. So let me give an example. A Gaussian relay channel is described as follows. YR is equal to some G21X plus some noise, and Y is G31X plus G21XR plus some noise, Z2. So what the receiver is getting is a linear combination, it's a weighted linear combination of what the transmitter and the relay are sending, plus some independent noise. So Z2 here is a standard noise, Gaussian noise, and Z1, which is independent of Z2, is also a standard Gaussian noise. This is an example. YR, so I have not included the term XR here because the relay knows what it has transmitted, so it can subtract it off. So YR, I have written YR as depending only on X, not on XR. So this is the description of a relay channel, but what is the communication problem? The transmitter has a message M in the set 1 to 2 to the NR. The relay does not know anything about the message at the beginning. So what the transmitter do is transmitter uses an encoder to convert the message M to a sequence XN and then sends the sequence XN over the channel. Now, the relay should also specify its input. Now, at time 1, at the beginning, relay doesn't know anything. So its input is some deterministic number, some constant. But at time 2, time step 2, the relay has observed YR at time 1. So its input at time 2 is a function of what it has received at time 1. And in general, at time I, what the relay transmits a function of its observations at time 1 to time I minus 1. And then the receiver gets YN and uses a decoder to reconstruct the message M. So we say that a rate R is achievable if this is achievable if for every epsilon positive there exists a block length n, an encoder, and a decoder such that the error probability, so an encoder for the transmitter and these functions, and then the functions f1 to fn for the relay, such that probability that m is not equal to m hat is less than or equal to epsilon. So this problem looks more difficult than a point-to-point communication because the relay node gradually learns about the message M and has to communicate what it has learned to the destination in real time. So there is some so what the relay gets is a noisy version of what transmitter has sent, so it does not have perfect knowledge of what has been sent, so it has to decide how it wants to what and how it wants to communicate to the receiver. So there is this feedback that XRI depends on the past observations of the relay that makes the problem difficult. And this problem is open. There are some, we know that certain rates are achievable and we have a converse. The cut-set bound, I'm going to describe it. There is a general converse for this, but in general, we do not know the capacity for the relay channel, the maximum achievable rate, because the rates that we know are achievable are strictly below than the rates that we know are not achievable. So the inner bound and the outer bound, the lower bound and the upper bounds do not match. Okay, Let me pause here because I'd like to answer any questions in case anybody has not understood what the definition of a code and capacity for the relay channel is. So take an arbitrary relay channel, Py, Yr given X, Xr. Then the capacity of this relay channel is bounded from above by the so-called cut-set bound. So cut-set bound is the best known upper bound for a general relay channel. It says that any achievable rate R is less than or equal to maximum over all joint distributions between X and XR of the minimum mutual information between X, XR, and Y, comma, mutual information between X and Y, YR given XR. And so to intuitively understand these two terms, the first term corresponds to a cut that separates the transmitter and relay from the receiver. So the information flow across this cut, intuitively speaking, is an upper bound on the capacity of relay channel and the flow of information from transmitter to receiver. So this mutual information between X, XR, and Y is an upper bound. The second term corresponds to the cut over here. It's the flow of information. It's a bound on the flow of information going out from transmitter X towards the relay Y and YR when we condition on the signal of the relay. To formally prove this bound, we proceed as follows. Take a code, an arbitrary set of encoder and decoders, an arbitrary encoder and decoder, and let's assume the message M is in the set 2 to the NR. Then I can write NR equals to entropy of M. By Fano's inequality, this is approximately equal to mutual information between M and Yn, because Yn is decoding the message M. Then by data processing inequality, this is less than or equal to mutual information between Xn, XRn, and Yn. And now, just as we proceed in the point-to-point channel, I can expand this term. This is blah, 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 blah. I can follow the same steps and say that this is less than or equal to summation I from 1 to Ni, Xi, Xri, and Yi. So this is the proof for the first term. It's essentially a point-to-point channel proof. Now for the second term in the cut-set bound, we proceed as follows. NR equals to H of M. This is approximately mutual information between M and Yn. This is less than or equal to mutual information between M and Yn, Yrn. And then I can write this as, using the chain rule, I can expand this. So this is summation I from 1 to N, mutual information between M and Yi, Yri, given Y 1 to I minus 1, Yr 1 to I minus 1. Just by the chain rule. And now observe that Xri is a function of yr1 to I minus 1. So I can throw in xri here, I can add it here, and then what I can do is I can bring up this term in the mutual information as follows. So this is less than or equal to summation I from 1 to n I m y 1 to I minus 1 yr 1 to I minus 1 and yri given xri. Now because xi m implies xn is a deterministic function of n, I can throw in xi here, and then one can argue, you can do it yourself, that this summation can be simplified as follows. Basically, this becomes mutual information between xi and yri given xri, and the second term vanishes in the chain rule. So I get this equation, and basically the proof of the cut-set bond, the main steps of the proof of the cut-set bond are these two derivations. Okay, now I want to introduce an auxiliary receiver. So y is the legitimate receiver, so I want to introduce an auxiliary receiver t. So this is x, this is xr, yr, and this one is the real receiver y, but I'm going to introduce a receiver, auxiliary receiver t. So, and to specify this channel, I need to specify the joint distribution of y, yr, t given x, xr. So when we fix the inputs x, xr, I will have a conditional distribution on t, y, yr. For some reasons, technical reasons that will become later if you go through the proof carefully, I want to assume that if from like this py, yr, t given x, xr, suppose I compute, I sum over y and yr, so this becomes probability of t given x, xr. So I want to assume that p of t given x, xr equals p of t given x. So t depends only on x. So I have this, essentially I have this Markov chain that xr to x to t is always Markov. All right, so with this auxiliary receiver, I can go back to this set of equations. So I want to replace y with t, so let me erase this part, and then I'm going to replace this with t, 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 and so everything goes through. Okay, so I'm interested in in R. I want to bound R from above. So NR was approximately mutual information between M and YN. So as before, I can write this as mutual information between M and Tn plus mutual information between M and Yn minus mutual information between M and Tn. So this part I know, the first part I know that I can bound it from above by summation I from 1 to n, mutual information between xi and ti yri given xri. The second term, I can expand it as summation I from 1 to n, mutual information between m and yi given past of y, future of t, all right. Now, I know that xi is a function of m, so I can throw in xi here. And because of the assumption that I made, so because of this assumption, we can actually bound this term, this second term, as follows. So summation I 1 to n I of xi ti yri given xri plus I of xi xri yi given y 1 to I minus 1 ti plus 1 to n minus I of xi xri and ti given y ti plus 1 to n. Let me call this wi. Now I can, so this, if you work this out, at the end we get the following bound. So what was the cut set bound? The cut set bound said that r is less than or equal to maximum p x xr. It was the minimum of two terms, I of x xr and y, plus I of x and y yr given, oh sorry, comma ix xr given xr. Now the new term that I have is as follows. It's I of x and t yr given xr. So I'm replacing y with t, but then I have to pay a penalty term, which is I of x xr y given w minus I of x xr and t given w. Okay, so this is the new term. And again, because of this particular assumption that I made on t, this assumption, because of this assumption that I made on t, I can one can show that this random variable wi, this it's called an auxiliary random variable. I have the following Markov chain, basically w to x xr to y yr is Markov. So this is our new bound using the auxiliary receiver approach. So before going to, so I want to discuss examples where this bound strictly beats the cut set bound. But before that, I want to pause here and see if there are any questions.
Hi, Amin, this is Prakash. May I ask a question?
Yes, please.
Can you scroll up a bit, please? Shagnik, maybe you're controlling the screen. If you can scroll up to the point where there was this assumption that was made, right here, yeah. So, I mean, two questions. One is, in these calculations, are you making any assumption that y and yr conditioned on X and XR is conditionally independent of T, or is that not pertinent at all?
No. The correlation, then I'm not making any such assumptions.
Making
Yeah.
an assumption.
No.
Now, the other thing is more of a general question. So what exactly is going on? What is this T getting us? I can see the calculations that you did, but eventually, where is the advantage coming from?
So when we introduce T, we can use the I mean, this is like from a mathematical point of view, you have more freedom, right? You can use past of T and future of T now when you are identifying auxiliary variables. So when you only have X, Y, and YR, you can only use past and future of Y and YR. But now you have more freedom. And this is like, so as a mathematical tool, this is the meaning. But in general, in other examples, you can see that T can be, so this auxiliary receiver approach can be a generalization of the Gini approach. You will see it in the broadcast channel later on. So T does not have any meaning. So it's not decoding anything, unlike the Gini approach. Yeah, so it's just a mathematical tool to write converses.
No, I understand that. I was just trying to see if I could think of conditions under which T would not be useful, right? And I couldn't see that immediately. That's what I had in mind. In other words, can we see what role T is playing from a statistical viewpoint by looking at conditions under which T becomes useless? Is that understood?
So
on the joint statistics, in other words, on the joint statistics.
Yes, I don't have a clear answer to this, but if you simplify this bound, for instance, you can compare it with lower bounds and see. I don't have a good answer to this, and I also want to mention that this restriction that I have put on T, you can relax it and get some other bounds. It's not so. We have some new results that we haven't published yet, and I have not talked about them here, but there's more going on here than like just this type of auxiliary receivers. Okay. Yeah, so I'm sorry, again, a very good question, but I don't have a good answer to it.
Thank you. Yeah.
Consider the following example. This is a Gaussian relay channel. Y is equal to G31 times X. So G31 is the gain of the channel from X to Y. G32 is the gain of the channel from the relay to the destination, and G21 is the gain of the channel from the transmitter to the relay. And Z and ZR are standard Gaussian random variable, independent. Z is independent of ZR. And I'm assuming that both X and the transmitter and relay have power constraint P, average power constraint P. So I want to plot a curve, and what I do is I fix P, G21, G31, and I want to vary G32. So what I want to do is I want to vary the link from relay to the destination. So as you can see, we have three curves here. The top curve is the cut-set bound. The blue curve is the new upper bound, and the curve below is the compress and forward lower bound. It's one of the known lower bounds on relay channel. As you can see, the new bound strictly improves over the cut-set bound. Now, when G32 is equal to 0, so if G32 is equal to 0, then this link is disabled from the relay to the destination, and you only have a link from transmitter to receiver. So as we increase G32, the capacity increases. The slope of the cut-set bound at 0 here, the slope is infinity for cut-set bound. But for R bound, the slope is finite. We formally prove this fact. This implies that the capacity which lies between this upper bound and the lower bound also has a finite slope at 0. And the reason that the slope of the cut-set bound is infinity because cut-set bound is allowing for arbitrary coordination between the transmitter and the relay. Okay, so this is all I wanted to say about relay. Now I want to move on to broadcast channels. Okay, now let us consider a broadcast channel. Broadcast channel is a communication system with 3 terminals. There is the transmitter, receiver 1, 2 receivers, receiver 1 and receiver 2. Transmitter sends the symbol X over the broadcast channel. The first receiver gets symbol Y and the second receiver gets symbol Z. So this is described by, the channel is described by a conditional distribution of PYZ given X. In a broadcast channel, the transmitter has 3 messages, M0, M1, M2. M0 and M1 are intended for the first receiver, and M0 and M2 are intended for the second receiver. So M0 is the common message, and M1 and M2 are private messages. A broadcast code consists of an encoder that maps the sequences M0, M1, M2 to a sequence XN. Then the first receiver gets YN, and we have a decoder that maps YN to M0 hat, M1 hat, and then another decoder that maps ZN to M0 hat hat and M2 hat. The error probability is the probability that any of these reconstructions are incorrect. And if any of them is incorrect, then we say that there is an error. So probability that M0 is not equal to M0 hat, or M0 is not equal to M0 hat hat, or M1 not equal to M1 hat, or M2 not equal to M2 hat. This is the error probability. And we compute this error probability assuming that M0, M1, M2 are independent, and so Mi, it takes values in a set of size 2 to the n Ri, and we say that Ri is the rate of message I. Here I can be 0, 1, or 2. So this is either M0, M1, or M2. We are interested in the set of achievable triples R0, R1, R2, such that for any arbitrary epsilon, there is a sufficiently large n such that we have a code whose error probability is less than epsilon. Just we define the capacity region just like we define the capacity in a point-to-point channel. Now, if R0 and R1 are 0, and we are interested in the maximum value of R2, then this problem is easy because we're just sending to the second receiver, and this becomes the capacity of the channel from X to Z. Similarly, if you want to just communicate to the first receiver, and we don't have any messages for the second and third receivers, then the maximum rate that we can send is the capacity of that link. However, if R0, R1, R2 are positive, then capacity becomes non-trivial, and in fact it's an open problem. It's not solved yet. So the difficulty is that we have 3 independent messages intended for different receivers, but we have to map them to the same sequence xn. So it's the optimal way to superimpose information. So let me pause and see if there are any questions about definition of the capacity for a broadcast channel. Okay, now I want to write outer bounds for broadcast channel. Suppose we have an arbitrary broadcast channel PYZ given X, and we have 3 messages M0, M1, M2. I can write NR0 equals to entropy of M0, and this is approximately mutual information between M0 and Yn, also approximately equal to mutual information between M0 and Zn. I can write NR1 equal to entropy of Y1, and this is approximately mutual information between M1 and Yn, because Yn is decoding M1. So by Fano's inequality, I can write this, but I can also condition it on M0, because this is approximately equal to entropy of M1 given M0, and we know that M1 and M0 are independent, so this is equal to entropy of M1. And NR2 equals to entropy of M2. This one I can write as mutual information between M2 and Zn, because Zn is decoding M2 given M0, M1. And this one I can write as mutual information between M2 and M1 and Zn given M0 minus mutual information between M1 and Zn given M0. So if we look at these 2 equations and add them up, we get NR1 plus NR2 is approximately equal to mutual information between M2, M1, and Zn given M0 plus mutual information between M1 and Yn given M0 minus mutual information between M1 and Zn given M0. And we know how to expand this difference. It's equal to summation I from 1 to n, mutual information between M1 and Yi given M0 Y1 to I minus 1, Zi plus 1 to n, minus mutual information between M1 and Zi given M0 Y1 to I minus 1, Zi plus 1 to n. So let me call this Wi. And now the question is, what inequalities can I write if I insist on using M1, M2, and Wi? So it turns out that we can actually write 8 inequalities that lead to upper bounds on rates or sum of R1 plus R0 or R0 plus R1, R2. So there are 8 inequalities that we can write using M1, M2, Wi. and they lead to UV outer bound for broadcast channel. And let me write two of these inequalities. So NR0, which is approximately equal to mutual information between M0 and Yn. This is less than or equal to summation I1 to N I of Wi Yi. So this is one inequality. And let me write NR0, another one, NR0, NR1, NR2. This is approximately mutual information between M0 and Yn plus mutual information between M1 and Yn given M0 plus mutual information between M2 and Zn given M0 and M1. And this is less than or equal to summation I from 1 to N I of Wi Yi plus I of M1 Yi given Wi plus I of M2 Zi given M1 Wi. So these are two of the inequalities that you can write. Two possible inequalities. And if you write the entire 8 inequalities, as I said, this leads to the UV outer bound for broadcast channel. And this is for a general broadcast channel with no structure, this is the best known outer bound. Okay, now I want to introduce an auxiliary receiver here. So this is my broadcast channel. We have an input X, an output, two outputs Y and Z. Now I want to consider an auxiliary output T. So I have P, Y, Z, T given X. So this is an extended memoryless channel. Now I had my M0, M1, M2, Xn, Yn, Zn. I can also consider Tn, right? It's so Yn, Zn, Tn are produced by passing Xn through this extended broadcast channel. And now again, I can observe that here in this inequality, if I look at just this part, I'm not using, in this inequality here, I'm not using the fact that M0 is decoded by Yn, or in the inequality here, I have not used the fact that the messages are decoded by the receivers. So when I introduce an auxiliary receiver T, I can do two things at least. So one is to replace, just formally replace Y with T, or replace Z with T. Okay, this is one possibility. Another possibility is to say keep Y and Z as they are, but replace M0 with M0Tn. Okay, so M0Tn is not decoded by Yn or Zn, but I can just formally, because I'm not using that fact in writing these inequalities, so I can just formally replace M0 with M0Tn. If we do, so there are two ways to do it, or we can also do a mixture of these two ideas. So these two lead to two different outer bounds. So this is leads to, let me call it new outer bound 1. We have to write all the equations, but it finally leads to new outer bound 1, let me call it, and this one leads to new outer bound 2. Each of these outer bounds can be shown to strictly improve over the UV bound for certain for particular channels. So I probably do the rest of the presentation over the PDF file for the paper. Okay, this discussion is just for the experts. This is the UV outer bound for a broadcast channel. Now observe that all of the mutual information terms, they involve either receiver Y or receiver Z. So if I take my broadcast channel and I pass Y and Z through erasure channels with erasure probability epsilon, and then I consider the channel P Y tilde Z tilde given X, this new broadcast channel, then what happens is that I would have Y tilde and Z tilde instead of Y and Z, and mutual information between W and Y tilde is just 1 minus epsilon mutual information between W and Y. And similarly for other terms, so the entire region shrinks by a factor of 1 minus epsilon, where epsilon is the erasure probability. Now, if we look at Marton's inner bound, it involves a binning loss term, which is a mutual information between auxiliary variables U and V. It does not involve receiver Y or Z. So this region does not necessarily shrink by 1 minus epsilon when I erase the outputs Y and Z. And in fact, we can show that it can shrink by more than 1 minus epsilon. This raises the question of whether the capacity region shrinks by 1 minus epsilon or more than 1 minus epsilon when we erase the outputs. And using the auxiliary receivers, we can write a converse, an outer bound that shrinks by more than 1 minus epsilon. And the reason is that this theorem 7 is the new converse, and here J is the auxiliary receiver. And so observe that when we pass Y and Z through erasure channels, we don't need to pass, we can take any arbitrary J and this bound holds. So J is not necessarily the output of an erasure channel. So if we keep using the same J that we were using before erasing Y and Z, we still get an upper bound, an outer bound. And we can formally show that this outer bound can shrink by more than 1 minus epsilon. So this question of whether the capacity can shrinks by 1 minus epsilon or more than that was asked by Young-Han Kim, and we would like to acknowledge and thank him for this question, because it led to all of these ideas. It was the starting point for this paper. I didn't get to talk about interference channels, but I just want to show you one picture. Okay. So this is consider a Gaussian Z interference channel. We have transmitters X1, X2, and assume that Y1 is X1 plus Z1, where Z1 is Gaussian noise, and Y2 is A times X1 plus X2 plus Z2, where A is less than 1, so it's a weak, we are in the weak interference regime. And this is a plot of the bounds. So this point is known as Costa's corner point. So we are setting R2 equals to C2, the capacity of the channel from X2 to Z2. And we're interested in the maximum R1, the maximum achievable rate R1. The bound over here is Polyansky-Woo's bound, which uses the Wasserstein continuity of entropy. It uses unconventional proof. It's based on an unconventional proof techniques. And this one is Sato's outer bound. Now, this curve in the middle, smooth curve in the middle, is our new bound. Observe that it's below Polyansky-Woo bound and the Sato bound everywhere, except the corner points, and this corner point is Sato's corner point. Okay, it also passes through Sato's corner point. Moreover, the slope at Costa's corner point is 0, it's flat for the Polyansky-Woo bound. So Polyansky-Woo bound is flat at Costa's corner point. However, our new bound, in our new bound, the slope is finite. So our bound strictly improves over Polyansky-Woo's bound around the corner point. So let me just quickly go through the statement of the main results. I presented an upper bound for the relay channel. If we specialize the bound to a Gaussian relay channel, we get the following proposition. The first two bounds are the cut-set bound constraints, and the third one is the new constraint. Now, this was the plot of the bounds with respect to the SNR of the link from the relay to the destination. And here the slope of the cut-set bound was infinity. In fact, this is like the function square root of x, which has slope infinity, but the new bound is a constant, is behaving like a constant times x close to 0. So it has a finite slope. And we actually have an explicit bound on the slope at 0 for the new bound. So it's finite. Okay, for the interference channel, here is our theorem. As you can see, there is an auxiliary receiver J here. And this was the plot for the new bound. The slope of Polyansky-Woo bound at 0 was 0. At Costa's corner point was 0. It was flat here, but our bound has a kink at Costa's corner point. And we actually prove this theorem, which gives a bound on the slope and formally proves that there is a kink. So finally, for broadcast channel, we have two auxiliary based, two outer bounds based on auxiliary random variables. This is the second outer bound. As you can see, it involves two auxiliary receivers, J and J hat. Okay, and this bound is actually a Gini-based bound. So the Gini approach to write outer bounds is a special case of the auxiliary receiver approach, because in the auxiliary receiver approach, the auxiliary we are not necessarily providing any new information to the receivers. However, the Gini approach, where we do provide some extra information to the receivers, can be understood as a special case of the auxiliary receiver approach. And this theorem is actually a Gini-based bound for broadcast channels. And each of the two bounds that we get for broadcast channels based on auxiliary receivers, each of them improves over the UV bound for certain examples. We find examples that this happens. Okay, let me conclude my talk here. So we have strictly improved outer bounds for relay, broadcast, and interference channels. Our bound for the Gaussian Z channel beats the bound recently obtained using unconventional techniques by Polyansky and Wu. The auxiliary receiver is a generalization of the Gini approach, as you could see from the second outer bound for broadcast channel. I should also note that there are some isolated previous works where we use auxiliary receivers, but we're using them in this work in a systematic manner. But there are some works that use auxiliary receivers to get bounds, like including the Gini bounds. Now, auxiliary receivers enable identification of more auxiliary variables during single letterization. What I mean by that, if I have two receivers Y and Z, the auxiliary random variables that I can identify is the past of Y, future of Z. It's just that. But if I introduce a new auxiliary receiver, I can also use the past and future of that auxiliary receiver, and that somehow helps to get a better understanding, get a better characterization of the trade-offs between rates. And there is much more to explore using this technique. We already have some other results for broadcast, for interference and relay channels. So we are certain that there are much more to explore using this technique. Thank you very much for listening to my talk. I would be happy to answer any question that you might have.
Amin, thank you very much. Very clear talk. Thank you very much. I enjoyed it, and I'm sure we all did. You were painstaking in presenting each step, and that has been very helpful. Are there any questions?
I just want to thank, I would be happy to answer questions, but I want to thank a few people, if it's okay.
Go ahead, please.
So first, I would like to thank the organizers again for inviting me to give this talk. Also, I want to thank Prakash for his kind introduction at the beginning of the talk. I want to thank the audience, and also I apologize if I have bored the experts. I forgot to thank Dr. Yasai because when we first found the relay upper bound, we had a complicated example, and Dr. Yasai alerted us to the fact that it also is helpful in the Gaussian, scalar Gaussian relay channel. And also Young-Han Kim for his question about broadcast channels. So I would be happy to answer any questions.
Okay. Any questions? So, again, thank you for very nice piece of work and very clear talk. I have one question, if nobody else has a question to ask. May I?
Sure, yes, please, yes.
The question is this. I saw the last theorem you had put in place with the auxiliary receiver. The question is, if there is hope, if there is to be hope that this approach will give upper bounds, which eventually turn out to be tight, then it means there has to be an achievability proof which somehow comes close to the regions that you postulate through this converse theorem. Now, what will be the meaning of the auxiliary random variables in the achievability proof? So that's what I was trying to get at earlier as well. In other words, right now, this is a mathematical tool. It gives you much more flexibility to get out of bounds. But eventually, if there's to be hope for an achievability proof, which will come close to these out of bounds, what role will these auxiliary random variables play in the achievability proof?
So again, I don't have a good answer for it, but if you consider for the relay channel, if you consider the partial decode and forward lower bound, and you look at this outer bound and compare it with the partial decode and forward lower bound, they're very similar. We could not find cases, I mean, new cases where they match, but they look similar. So in achievability proofs, we also sometimes use auxiliary random variables. So, but so the thing is, we do not know any particular channel where the new bound is tight. With this auxiliary receiver approach, it's tight, and it's also unclear what is the best choice of auxiliary receiver, right? So for each auxiliary receiver, we can write a bound, but it's not clear how to optimize over auxiliary receivers, the best possible bound that we can get. So again, it's a very good question. I'm sorry, I don't have a clean answer to it. I think your microphone is off.
Yeah. So if there are no more questions, then I thank Amin once again on behalf of all of us organizers, Shagnik and Ajay and Zitan and Adway and Sasha and me. So thank you very much, and we'll see you all at the next seminar 2 weeks from now. Thank you again very much, Amin.
Well done. Thanks, Amin.
Stay safe and stay healthy, and we'll see you again 2 weeks. Bye.